So thank you very much, David, and to the organizers. I hope I can prove David right. So this is a talk about alpha particle modeling and stellarators, but I'm going to frame it more generally, so let me motivate the problem. There are lots of people involved in this at this point. Ivan is my graduate student. Max is here, so he's a postdoc at UT. Dan Messenger, he started working on this with me when he was still at CU Boulder, but now he's at Los Alamos. And Leo Cabral, he's at Type 1 Energy. He's a recent addition to the project. The general setting is this. The simplest type of two-scale dynamical system is a so-called nearly periodic system. It's a system of ordinary differential equations with a right-hand side that depends on a small parameter epsilon. And the idea is that when epsilon goes to 0, this right-hand side should limit to this x0, and the solutions of this limit ODE should all be periodic. So that's what a nearly periodic system is. The example of this type of system that we all care about in this room is charged particle dynamics. So here I'm forgetting the electric field and effects of relativity. But you can see the way I've written it here, when you send epsilon to 0, all that happens is that the position of the particle remains fixed and the velocity spins around the magnetic field vector at that particle's position. The most sophisticated theory at the moment for handling this type of system applies in the limit where epsilon, this parameter that appears on the right-hand side, which is quantifying scale separation, timescale separation, is very small. And the theory, as I'm going to describe it here, is due to Martin Kruskal. So what Kruskal showed is that if you write your system in terms of variables where one of them is a fast phase, and the rest are grouped in this letter sigma, there's a normal form transformation. In other words, there's a sequence of near-identity coordinate transformations on phase space that changes you from the unbarred zeta and sigma variables to the barred ones. And what's special about the barred ones is that the right-hand sides of the ODEs now no longer depend on zeta bar. After doing this coordinate transformation, there's a one-way coupling between the fast phase and the slower sigma bars. And that one-way coupling implies that the equations of motion for the sigma bar, the slow variables, close on themselves. So there you have dimensionality reduction, right? So Kruskal showed this in this paper from 1962. And this is still the most sophisticated take on this type of system. But again, it only applies in the case where epsilon is exceedingly small. That slow motion, the equation of motion for the sigma bar, in the context of the charged particle motion, well, that corresponds, of course, to the guiding center. So the sigma bar would be this red curve, while the blue, which is the cyclotron dynamics, would be the whole system. The problem with this theory as it stands now is that when epsilon gets larger, there's a problem. The whole theory is based on asymptotic expansions. And asymptotic expansions have this property that as you decrease epsilon, you can include more and more terms in the series and still get useful information out of them. But as epsilon gets bigger, the number of terms that are useful in that series gets smaller. So the truncation, the optimal truncation order, it gets smaller as epsilon gets bigger. And if epsilon gets too large, you can have what I like to call collapse of optimal truncation order, where the truncation order might go from something that you like, maybe 3 or 4, all the way down to 0, where only the leading term is doing anything even close to right, and it still might be very bad. So this is a problem in principle. But I want to argue that it's a problem in practice as well. So in the next few slides, I'm going to summarize some work that I did not do. Work done computing loss fractions for alpha particles in various reactor-scale stellarator designs. And the idea behind each of these calculations is to compare the predictions of full orbit theory, the full Lorentz force model, to guiding center predictions, which are the state of the art. So in this first example, so this is coming from this master's thesis. I don't know how to pronounce the last name. Could someone help me? Asunsen. So this is his master's thesis. In that thesis, one of the things he did, amongst others, is to push guiding centers and full orbits in the Aries CS design. And he's chosen parameters so that the slowing down time is 67 milliseconds. And what he's done is he's plotted the loss fraction as a function of time for both full orbit, which is in the red, and guiding center, which is in black. And what he finds is that after 1 millisecond, which is much less than the slowing down time, there is more than 100% difference in the discrepancy. There's a more than 100% discrepancy in the loss fraction between full orbit and guiding center. Here's another one. So this is work due to Rodriguez. It's not this one. How many cyclotron orbits? I don't many. I don't know. I don't know off the top of my head. But you can see it's like a tenth of a slowing down time. Okay, so then here's this calculation from Rodriguez, not our Eduardo, who's here. Again, amongst the reactor scale configurations he considered, Aries was included, but there are also a number of others. And again, the punchline here is that there are significant discrepancies between the full orbit and the guiding center predictions. And here's just one more. So this is from a poster by Leo at APS this last year. And so this is looking at configurations that were not optimized for high confinement. So this was a configuration that you might encounter in the process of optimizing a stellarator. So it's a configuration with high alpha particle losses. And again, what Leo found here is that there are large discrepancies between the full orbit and the guiding center predictions. Now, there can be lots of reasons for why this discrepancy might exist. But a reasonable one is that we're in this regime where the optimal truncation order for the guiding center asymptotics is collapsing. That's my claim. And I can back this up with some detailed calculations of our own. So here what I'm doing is I'm pushing full orbits in a Z translation symmetric magnetic field. So I'm just taking a magnetic field that just points along the Z axis, and its strength depends on X and Y. So this is the paradigm for axisymmetry. So an exceptionally simple type of field. And what I'm plotting here is I'm plotting phase portraits in black for the full orbits for 3 different values of epsilon, 5%, 15%, and 27%. So superposed on top of the black curves, you can see the orange. Those are the predictions from guiding center theory, traditional guiding center theory. And even at the 5% level, you can see there are pretty significant deviations between the drift surfaces for the full orbits and the guiding centers. It's more extreme at 15%. And then when you get all the way up to 27%, which is a very extreme case, you even start to see chaos. And where you have chaos, there's definitely no semblance of any sort of guiding center model that you could use. On the bottom here, what I'm plotting is time traces of 3 different truncations of the magnetic moment adiabatic invariant. So in general, the magnetic moment adiabatic invariant is a whole asymptotic series. And in this type of field, you can actually compute the first 3 terms without much difficulty, the first 3 terms in the series. So black is the 0th order truncation, the usual expression we use for mu naught. Red, that's including the first 2 terms in the series, and blue is including the first 3 terms in the series. And what you can see is that at 5%, we're getting between 10 and 15% type of errors in the lowest order truncation. But if we did go to the higher order guiding center theory, we do see this improvement. You can see the red and the blue, they get successively smaller. So as we include more terms in the series, things are getting better at this level. But already at epsilon of 15%, we can see that that improvement, and particularly improvement from going to second order to third order, it starts to degrade. And you might argue here that the optimal truncation order in this system is maybe 2, as in the first 2 terms. You know, red is certainly doing better than black, but blue is only marginally better than red. And then when you go all the way to the case of epsilon 27%, you see everything's out of order. So there's definitely a total collapse of the optimal truncation order in that case. Now, why did I pick these values of epsilon? So if you look at stellarator reactor designs, and you estimate the epsilon, so the epsilon in this case is rho over L. It's the typical particle gyro radius divided by the scale length of the field. If you do an estimate of rho over L for alpha particles in a stellarator, where you use as the scale length the quoted minor radius for the design, what you'll typically find is something like epsilon of 3%, between 2 and 3%. But the problem with that estimate for epsilon is that it's an underestimate. The way that estimate is usually formulated is you would take, for each polyidal cross-section, you compute the circumference, and you divide that by 2 pi to get a length, and then you'd average that over a toroidal angle, and this would give you some semblance of a minor radius, some effective minor radius. But this way of estimating epsilon underestimates it because it doesn't account for the fact that some of the cross-section can be extremely shaped. So the local epsilon can actually be a lot bigger than that 2 or 3% figure. 15% is about a factor of 5 bigger than 3%. So here's the problem. Here's the real subject of this talk. Is it possible to formulate an accurate slow model in this sort of in the sense that I described in Kruskal's theory, when we're in this marginal regime, where we're starting to see this collapse of the optimal truncation order? And the answer, I claim, is yes, at least in the Hamiltonian case, which is the case that's relevant to alphas and stellarators. And what do I mean by the Hamiltonian case? Well, it means that ODE that we started with, that x epsilon that defines the nearly periodic system, this should be a Hamiltonian vector field with respect to some Poisson bracket and some Hamiltonian function. So this is what I want to argue. To construct the argument, first, I'm going to give you the formally exact picture of how to do this, or a formally exact picture of how to do this. So that'll be the first part. The second part, I'm going to give life to the exact picture by showing work that I've been doing with Ivan and Max at UT, where we're actually able to take the formally exact picture and compute with it and get useful results out. So the way that I approach this formally exact picture, or the way that I approach non-perturbative guiding center theory, is I exploit this observation due to Kruskal that the essential ingredient that explains why his theory works is due to the presence of a hidden symmetry. This is a very early example of hidden symmetry. So the hidden symmetry in this case, when we're in these normal form coordinates, is just translation in that phase variable zeta, well, the phase variable zeta bar. So you can see that if you take a solution of this system of equations here in the normal form coordinates, and then you translate the zeta variable by this constant theta, you get another solution. So this is an example of a symmetry of a system of ordinary differential equations. Of course, this symmetry looks very simple in these normal form coordinates, but back in the original coordinates that we started with, it's going to be something much more complicated. And Kruskal was able to show how to compute that symmetry order by order in epsilon. So more generally, I need to tell you what I mean by symmetry, just to be precise. And the only type of symmetry that I'm going to care about in this talk is a so-called U1 symmetry. U1 is a group, it's the circle group. It's the group of phases. So a U1 symmetry for a system of ordinary differential equations, it's a one-parameter family of mappings phi sub theta. So the parameter is theta, and phi theta maps phase space into itself. And this thing has to have three properties. When the parameter is 0 or 2 pi, we should get the identity map. So if you rotate by the angle 0, you shouldn't actually move any points in phase space. And then if you rotate by theta 2 and then by theta 1, that should be the same thing as rotating by the sum of theta 1 and theta 2. Okay. So it's a one-parameter family of maps such that it maps solutions of that system of equations into other solutions. So that's what I mean by U1 symmetry. Another useful piece of jargon here is the notion of a U1 orbit. So if you have one of these U1 symmetries, if you have that family of mappings phi sub theta, you can take any point in phase space z, and then you can look at all the possible rotations of it under this one-parameter family of mappings. So those would be the z primes. The collection of all those rotations of z is called the U1 orbit through z. So these are circles in phase space. And every point in phase space, if you have one of these U1 symmetries, will have one of these orbits passing through it. So this decomposes the whole phase space into a bunch of circles, topological circles anyway. And last bit of definitions here. The infinitesimal generator of of one of these U1 symmetries is just this vector field. The idea is that if you want the vector field R at the point z in phase space, well, you rotate that point z by this amount theta, and then you differentiate in theta at theta equals 0. So you sort of look at the theta velocity, the initial theta velocity of the U1 orbit through that point. So that's the infinitesimal generator. This is the vector field that points along these U1 orbits. That's the way to think about it. Okay, so I said that in Kruskal's theory, this hidden symmetry was hidden in particular. So why did I say it was hidden? Well, I already mentioned this. The reason that the symmetry in Kruskal's theory is hidden is because if you're not looking at the system in those normal form coordinates, it's entirely not obvious. I said that it explains his theory. I said that the presence of this hidden symmetry is the reason that Kruskal's theory works in the first place. So what do I mean by that? Well, what does Kruskal's theory get you? It gets you two things. It gets you dimensionality reduction, because you're able to forget that fast phase. And it gets you a timescale reduction. So you don't have this separation of timescale anymore. That's because you don't have to resolve the dynamics of the fast phase anymore. Well, the dimensionality reduction, this is entirely because of the symmetry. Anytime that you have a symmetry of a system of ODEs, a continuous symmetry, in particular a U1 symmetry, you get a reduction of the dimensionality of phase space by 1. So this is just from general symmetry reduction principles. And now, as far as the timescale separation is concerned, how is that explained by this symmetry? Well, the eliminated dimension from this symmetry is precisely the fast degree of freedom. So how do I want to use this perspective on Kruskal's theory to push into the non-perturbative regime? My idea is let's ditch the asymptotic